Imagine a world where rivers once carved canyons across a rust-red desert, where lakes glittered beneath a thicker sky, and vast oceans may have lapped against alien shores. Today we uncover the evidence that Mars was once a watery world, from winding valley networks to mineral clues hidden in its rocks. In the next minutes you'll see how ancient riverbeds were sculpted, what lakebed deposits tell us about standing water, which minerals like clays, sulfates, and carbonates reveal about past chemistry, and why scientists think a northern ocean might have shaped the planet's stark hemispheric divide. Stick around to learn what this means for the chance of past life, and if you enjoy diving into Mars's secrets, hit subscribe and join the exploration. Imagine looking up at the rust-colored sky of Mars and seeing not a barren desert, but a world once carved by rivers, dotted with lakes, and perhaps even draped in shallow oceans. Today the planet is a frozen wilderness, its surface scarred by dust storms and impact craters, yet beneath that red veneer lie clues that water once flowed freely across its landscape. Those clues come in the form of dried river valleys, ancient lakebeds, and mineral deposits that only form in the presence of liquid HO. Scientists have pieced together this story from orbiting spacecraft, rovers on the ground, and even meteorites that fell to Earth, each revealing a different chapter of Mars' hydrologic past. Understanding where that water went, how long it lingered, and what conditions allowed it to exist is more than an academic exercise. It directly informs the question of whether life could have taken hold on the red planet. If water was stable enough to carve canyons and sustain lakes, then the ingredients for life, liquid water, energy, and essential chemicals, may have been present together for millions of years. As we follow the trail of evaporites, clay minerals, and shoreline features, we edge closer to answering one of humanity's biggest mysteries: did Mars ever host life, and what can its dry present tell us about our own planet's future? Having sketched the broad picture of a wetter Mars, we now zoom in on the planet's surface where the evidence of flowing water is etched in stone. Across the southern highlands, branching patterns spread like the veins of a leaf, forming what scientists call valley networks. These dendritic systems begin modestly as shallow gullies on crater rims, then converge and widen, carving channels that can stretch for hundreds of kilometers before terminating in low-lying basins or fading into the dusty plains. Their tributary structure mirrors rivers on Earth, where rain-fed runoff carves the landscape over time. The uniformity of their angles and the smoothness of their floors suggest a sustained flow, not a flash flood, implying a climate that could support precipitation or groundwater seepage for extended periods. High-resolution images reveal inner channel walls lined with layered sediments, hinting at periods of deposition when the water slowed and dropped its load. Some valleys even display subtle meanders, the sinuous bends that only develop when water flows gently enough to erode the outer bank while depositing sediment on the inner side. Together, these features paint a picture of ancient rivers that once meandered across Mars, sculpting the terrain we see today. As we follow these water-carved pathways, the next clue lies in the basins they fed, where standing water may have lingered long enough to leave behind mineral signatures waiting to be uncovered. After tracing the winding channels that once carved Mars' surface, we turn our gaze to the quiet basins where those waters finally settled. Here, the landscape tells a different story, one written in fine-grained strata and mineral signatures that betray the presence of standing lakes that persisted for millions of years. Orbital spectrometers have spotted expansive deposits of clays such as smectite and sulfates that only form when water lingers, allowing chemical reactions to proceed slowly beneath a protective blanket of sediment. High-resolution images reveal rhythmic layering, each thin sheet a seasonal record, like the pages of a diary capturing wet and dry cycles. In places like Gale Crater's Yellowknife Bay, the Curiosity rover drilled into these layers, finding finely laminated mudstone interspersed with calcium sulfate veins, clear evidence that water not only pooled but also circulated through the subsurface, altering rock chemistry over time. These lakebed archives suggest that Mars once hosted stable, freshwater environments capable of supporting life, at least intermittently. As we piece together this aqueous puzzle, the next question looms: what became of the atmosphere that could sustain such lakes, and how did the planet's climate shift from wet to arid? The answer lies hidden in the thin air above us, waiting to be uncovered. Future missions will drill deeper, seeking isotopic clues that reveal how much water was lost to space and how much may still linger locked in subsurface ice. Having traced the ancient river valleys and lakebeds that once dotted the Martian surface, we now turn our eyes to the rocks themselves, where chemistry leaves a lasting imprint. On Earth, water's interaction with basalt produces distinct mineral suites that record its temperature, acidity, and dissolved ions. The same principle holds on Mars. Orbital spectrometers have mapped extensive deposits of phyllosilicate clays, such as smectite and chlorite, in the Noachian highlands. These clays form only when water is relatively neutral to mildly alkaline and persists long enough to alter volcanic rock, suggesting that early Mars hosted habitable, lake-like environments with pH values near 7 to 8. Moving forward in time, the mineral record shifts. Vast expanses of sulfate salts, gypsum, kieserite, and jarosite appear in regions like Meridianiplanum and Valles Marineris. Sulfates precipitate from acidic, evaporating brines. Jarosite, in particular, forms under strongly acidic conditions, pH 3, and signals a dramatic drying trend as surface water became scarce and increasingly salty. Finally, scattered carbonate outcrops, detected in the Nili Fosse and around the Huygens crater, hint at brief episodes when carbon dioxide-rich atmospheres allowed liquid water to linger long enough to trap Co as solid carbonate, implying transiently milder, less acidic waters. Together, these mineral fingerprints chart a planetary evolution from neutral, clay-forming waters to acidic sulfate brines, and finally to the fleeting carbonate-bearing moments that still whisper of Mars' wetter past. Building on the evidence of ancient rivers and lakes that once carved the Martian surface, scientists now turn their gaze to the vast northern lowlands, a region that sits several kilometers below the southern highlands. This striking elevation difference, known as the Hemispheric Dichotomy, has long puzzled planetary geologists, but it also offers a tantalizing clue. If Mars ever hosted an ocean, its waters would have pooled in this deep basin. High-resolution orbital images reveal a series of subtle, linear ridges and scarps that run parallel to the lowland edge, resembling the shoreline features seen on Earth where waves have eroded coastal cliffs. In addition, spectral data detect minerals such as clays and sulfates that typically form in standing, saline water, further strengthening the ocean hypothesis. Some researchers point to the presence of possible tsunami deposits, large, boulder-laden lobes that appear to have been flung inland by massive waves, perhaps triggered by meteorite impacts into a northern sea. While the idea remains debated, the convergence of topography, morphology, and mineralogy paints a compelling picture of a northern ocean that may have covered up to a third of the planet billions of years ago. As we piece together these ancient shorelines, the next question looms: what drove the dramatic climate shift that eventually drained this water, leaving Mars the arid world we see today? Having traced the story of Mars' vanished rivers, lakes, and seas, we can now step back and ask what all that water really meant for the planet's capacity to host life. The geological record tells us that liquid water was not a fleeting splash but a persistent presence, carving valleys, depositing sediments, and even forming shorelines that lingered for millions of years. Those long-lived aqueous environments provided the chemistry, stable temperatures, pH-neutral waters, and a steady supply of essential elements like carbon, nitrogen, sulfur, and phosphorus that on Earth are the foundations of habitability. In addition, the detection of mineralogical signatures such as clays, sulfates, and carbonates points to water-rock interactions that could have generated energy sources for microbes, much like the hydrothermal vents that nurture life in our oceans today. While we have yet to find direct fossils or organic molecules on Mars, the convergence of hydrological, mineralogical, and climatic evidence paints a picture of a world that, for a substantial stretch of its early history, possessed the key ingredients necessary for life to arise and possibly endure. Looking ahead, the next generation of rovers and sample return missions will target those ancient lakebeds and river deltas, seeking the chemical clues that could finally answer whether Mars was once a living world. These investigations could reshape our understanding of life's potential beyond Earth and inspire the next steps toward human exploration of the Red Planet. Today we explored how Mars once hosted rivers, lakes, and even vast oceans, revealing that the Red Planet was far wetter and more Earth-like than we imagined, suggesting that its ancient climate could have supported microbial life long before it turned into the dry desert we see today. If you enjoyed this dive into Mars' watery past, please smash the like button, hit subscribe for more planetary mysteries, and in the comments tell me, what do you think happened to all that water? Did it escape to space, freeze underground, or something else entirely?